So hi everyone. I'm here to talk about my research, which consists of measuring the expansion rate of the universe from a physical phenomenon with the help of machine learning. So here's the overview. So first I'll talk about the Hubble constant, which is just another name for the expansion rate of the universe. It's also called H0 for short. I'll talk about time delay cosmography, which is the method that we use to infer it. I'll describe some technical challenges with this method and how machine learning tools can help us with those issues. I'll show some preliminary results and talk about the next steps. So first, I would like to give you an intuition of what is the expansion rate of the universe. So in this analogy, the universe is a blueberry muffin. The batter is space, while the blueberries are galaxies. So as time goes by, the batter cooks, and because it cooks, it expands. And by doing so, it moves away the blueberries away from each other. So it's the same thing in the universe. As space expands, it moves away the galaxies from each other. We can see this with some observations. And the rate of this expansion is the Hubble constant. And it's a crucial parameter to determine cosmological distances and the age of the universe. So right now we have two main measurement methods to evaluate H0. The first one uses the cosmic microwave background, which is a radiation coming from the early universe. It also relies on a theoretical cosmological model. The second method uses type 1a supernova, which are explosions of stars. The problem is both methods don't yield the same value. So on the left, in blue, we have the result for the cosmic microwave background, and in red, on the right, we have the result for the supernova. So there is a discrepancy, and it's not just because of some experimental error. It's really significant. So we don't know if we have a problem with our cosmological model or with our comprehension of supernova, but we would like to have another method independent from these two that could help us to solve this discrepancy. And then we would know where to look for our error. So one of the candidate method is time delay cosmography. So let's see how it works. First, it involves quasars. Quasars are celestial objects that have the particularities of flashing and of being detected as point sources by our telescopes. So let's say that we have a galaxy between our telescopes and a quasar. Then the galaxy, the mass of the galaxy will distort space-time around it. So the light, one flash of the quasar will be able to take many paths through this distorted space-time. Because of that, our telescope will see the quasar at different positions and at different times. And this is interesting because these time delays depend on a cosmological distance, which is inversely proportional to H0, and a lensing potential that is caused by the lensing galaxy. So to infer H0, what we need to do is to measure these time delays and to reconstruct the lensing potential. And from the image that we detect, that we observe. And that's the real challenge. Because the traditional way to reconstruct this potential is really time consuming. So we build a simulator from our lensing model. Then we initialize some parameters and we create a simulation. Then we compare it to the real image that we observed and we update the parameters to have a better fit. And then we repeat this process until the produced simulation closely reproduces the real image. But this method can take, inferring H0 from this method with just a few lenses can take several months with the supervision of an expert. So time is really an issue because to infer H0 with a great accuracy, precisely, we need a large data set. And the Robin Observatory will start in 2023 its legacy survey of space and time, which will collect 500 petabytes of astronomical data in its 10 years of activities. And we expect it to detect 8,000 lens quasars, which would take hundreds of years to infer each knot from such a large data set. Thankfully, we already have machine learning tools to accelerate the analysis. So here is an example of a convolutional neural network taking as input the lensed image of a galaxy and outputting the value of 3 parameters that describe the shape of the lensing galaxy. So we have the real value versus the predicted one, and you can see that they agree pretty well. The problem with CNNs is that it's hard to quantify their uncertainties. Well, on the uncertainties on the prediction. So some have used Bayesian neural networks instead, but they require Markov chain Monte Carlo, which are a sampling procedure that is really expensive. Another alternative is an approximate Bayesian neural network, but that heavily relies on its variational distribution. So we have no guarantee to fit accurately the distribution of our parameters. But let's go back to our problem. So, okay, I said we have to measure time delays and then reconstruct the potential to infer each knot. But what if we could just directly infer each knot from the image and the time delays? So that's what we're trying to do with simulation-based inference. And before explaining what is simulation-based inference, I just want to say that it has a solid statistical basis. It provides an unbiased posterior estimation, and it's really efficient for a single parameter. It could be hard to conduct with more, but in our case, we just want to infer each knot, so it's perfect. And it offers more diverse tests of robustness. So how does it work? Okay, so let me walk you through this. We have a simulator that produces images and time delays from some lensing parameters and the value of each knot. So we use it to create 2 data sets. The first one has images and time delays that were produced with an H-knot value that was drawn from distribution at each simulation. The other set, well, in the other set, all the simulations share the same value of H-knot. So we want to train a classifier to distinguish between these 2 sets. So our classifier have to tell, does this simulation was created from the fixed value of H-knot or any other else? And the inputs are the image, the time delays, and the value of H-knot. And it has been proven that the optimized decision function of this classifier can be used to as an estimator for the likelihood ratio, which will give us the distribution for H-knot. So, oh yeah, sorry, I just forgot to mention, to measure H-knot from this, we just have to give real observation to our classifier with the many values of H-knot, and then we will have a distribution with an uncertainty. So until now, well, I will talk about what I've been doing until now. So these are examples of simulations. So on the left, we have the light profile of a galaxy. Sorry, I think I just drink water real fast. Yeah, so we have the light profile of the galaxy. Then the second image is the mass distribution of the lens galaxy. And here we have the image that we would see from the Earth if this galaxy was in front of this one. And the last image is kind of the same thing, so but instead of a galaxy, it would be a quasar being lensed. This is the architecture of our classifier. So we input images, and they go through many convolutional layers that were inspired by the overfeed network. The time delays and the H-knot value go through linear layers, and that they are all regrouped in the last linear layer and before the final output. And here are the learning curves of our classifier. So as you can see, the loss is decreasing for both sets, and the accuracy achieves 98%. So it's doing great. We know that we have a classifier that can be a good estimator for deviation of value. So for the future, we have to conduct some sanity checks to make sure that our network is learning from the relevant information. We still have to conduct the inference. So to be sure, we'll try first to predict H0 from a set of mock data to make sure that our method works. Sorry, I have to drink again. Then there are many ways to conduct the likelihood ratio trick. And we'll have to find the one that is, sorry, the more suited, the best suited one for our problem. And we have to do more realistic simulations. So I think I will stop here because I cannot speak anymore. Sorry about that. So thank you for listening, and I'll be happy to answer questions.
Thank you a lot, Eve. It's hard to talk. I have my water glass as well as all the time. Take 2 minutes if you need to just hydrate your voice. It happens. So if you could put up your summary slides, I'd be interested to read it. Maybe we can like take more info on that slide. So for the Hubble constant, the tension on an important parameter for cosmology. Okay, the Hubble constant, yes, is an important parameter. Then another point is the time delay cosmography is a measurement method independent of CMB and SNE-LA.
Yeah, so it's independent of the two. Yeah, I'll do. So yeah, so the Hubble constant is an important parameter for cosmology, and we have this tension on some measurements. And time delay cosmography is an independent method of the ones creating these discrepancies, so it could be really useful. But we have to make it to develop an efficient method to analyze the data, because there's a huge amount of it coming in. But we already have machine learning tools that can help us to accelerate the analysis, and it's also a robust inference framework. So we already have a training classifier for estimating H0. So we just need to redo it with more realistic simulations, because we want it to work also on real data, and to find the optimal inference framework.